Welcome to our exploration of stacks and queues. First up, let's dive into how we implement these data structures. A stack is like a stack of plates. You can only add or remove items from the top. Think of push for adding an item and pop for removing it. For example, in a browser, pressing back navigates to previous pages by popping them off the stack. On the other hand, queues are more like lining up at the grocery store. First in, first out, FIFO. Enqueue adds items to the end of the line, while dequeue removes from the front. Imagine a printer queue. Jobs print in the order they arrive. Both stacks and queues have their unique roles in programming, making them indispensable tools for problem solving. Welcome to our journey into the world of data structures. Today, we're diving deep into two fundamental ones: stacks and queues. First, let's introduce what these are. Then, I'll show you how to implement them in code. Next, we'll explore real-world scenarios where each shines. We'll also compare their differences and similarities. To keep things engaging, there will be a quiz to test your knowledge on stack or queue usage. Finally, we'll wrap up with the key takeaways from our session today. Ready? Let's get started. Welcome to our exploration of the stack data structure, which follows the last in first out LIFO principle. Imagine you're stacking books. The last book you place on top is the first one you take off. Let's dive into its operations. Push adds an element at the stack's top, like placing a new book on your pile. Pop removes the topmost element, just as if you were taking the highest book off. The peek operation lets you see what's on top without removing it, like peeking at the tallest book. Lastly, empty check tells us whether our stack is empty, much like checking if there are any books left. These operations make stacks incredibly useful in scenarios where order matters, such as function calls or browser navigation history. Welcome to our lesson on implementing a stack in Python. A stack is a data structure that follows the last in first out LIFO principle. Today, we'll use a list as our underlying data structure. Let's dive into the code. We start by defining our class with an initializer that sets up an empty list for us. The method checks if the stack is empty. The method adds an item to the top of the stack, while removes and returns the top item. Think of it like a stack of plates. Lets you see what's on top without removing it, and tells you how many items are in your stack. This setup is perfect for scenarios like managing function calls or parsing expressions. Welcome to our tutorial on stack implementation. Let's dive into the code we have here. We start by creating an instance of our stack class with. Then, we push two elements onto the stack using the method A and then B. The final line reveals what's currently on top without removing it. If you run this code, you'll see B printed out because in a stack, the last element pushed is the first one to be accessed. This principle is known as LIFO, last in, first out. This makes stacks perfect for scenarios like managing function calls or parsing parentheses. Now that we've seen how our stack works, let's explore more of its fascinating applications and internal mechanics in our next slide. Welcome back to our journey through data structures. Today, we're diving into queues. A queue is like a line at the grocery store, first in, first out, FIFO. Imagine you're adding items. That's an enqueue operation, where elements are added to the end of the queue. Want to get something off the front? That's a dequeue operation, removing the element at the head. We use two pointers. Front marks the start and rear tracks the end. Think about real-world examples, printing jobs in a printer or tasks in a background process. They all follow this FIFO principle, making queues incredibly useful for managing tasks and operations efficiently. Welcome to our tutorial on implementing queues in Python. A queue is a linear data structure that follows the FIFO, first in, first out principle. We'll use a list as our underlying data structure for simplicity. Here's how we define our queue class. Inside, we initialize an empty list with. The method checks if the queue is empty by comparing self.items to an empty list. For adding items to the queue or enqueuing, we use and insert the item at the front of our list. To remove items, we dequeue them from the end using which removes and returns the last element with. And to get the size of the queue, we simply return the length of self.items. Let's move on to how this can be used in real-world scenarios. Great. Now, let's see how this queue implementation works. We start by creating an instance of the queue class with. Then we add two elements to our queue using the enqueue method. First, A, and then B. By calling, we remove and print the first element from the queue, which is A. As per the FIFO, first in, first out, principle. This simple example demonstrates how data is managed in a queue. For instance, if you were managing tasks for a printer, Task A would be printed before Task B. That's it for our quick look at queue implementation and operations. Stay tuned for more on stacks and queues. Let's dive into an example using a stack to simulate the browser back button functionality. In this scenario, we're implementing a class called. When you visit a new page, it gets pushed onto our stack. To go back, we pop elements from the stack based on how many steps you want to move backward. Here's what each method does. The constructor initializes our stack with the homepage URL. The method adds a new URL to the end of our stack. And finally, the method allows us to navigate backwards by popping URLs off the stack until we reach the desired history point. This example showcases how stacks can be used efficiently for managing sequences like browser history. Welcome back to our tutorial on stack and queue implementation. Now, let's dive into an example using the browser history. Here's what we're looking at. We have a browser object that acts like a stack, where each visit is pushed onto it. When you call, it's similar to pushing page 1 onto our stack. And then when we do, it's equivalent to popping from the stack, bringing us back one step in history to page 1. This stack-like behavior of the browser back button is a perfect illustration of how stacks work, where elements are added and removed following the last in, first out, LIFO principle. Think about it like this. Every time you visit a new page, that page gets pushed onto the top of your history stack, and when you click the back button, it pops from the stack, bringing you to the previous page. Welcome back to our tutorial on stack and queue implementation. Today, we're going to compare the wrong way of doing things with the right approach. First up, storing stack items in a global variable. While this might seem convenient at first, it can lead to unexpected behavior and bugs, especially when multiple parts of your code are trying to access or modify the same data. The recommended practice is to encapsulate your stack within a class, providing methods for push, pop, and peek operations. This keeps your data organized and makes your code more maintainable. Moving on to our second comparison. Not using the method when you need to dequeue an item. In a queue, should be used to remove and return the front element, ensuring that elements are processed in the correct order. Failing to do this can lead to incorrect behavior, as elements won't be removed properly, disrupting the queue's functionality. Always use the appropriate methods for each data structure to ensure everything works smoothly. Alright, let's dive into an interesting scenario. Imagine you're using a list to both implement a stack and a queue. So, if we think about the stack operations, pushing or popping elements, they'll be super efficient at O1, just like they should be in a stack. But here's where it gets tricky. When you try to perform enqueue or dequeue operations on this same list, things aren't as smooth. The time complexity will degrade to O(n) due to the way lists handle insertions and deletions at arbitrary positions. This means that every time you need to add or remove elements from the middle of the list, it can take a lot longer than expected. So, remember, while stacks might work just fine, queues won't be as efficient in this setup. Welcome back. Let's dive into the world of stacks and queues, starting with our first comparison. Stack versus queue. Think of a stack as a pile of plates. You can only add or remove a plate from the top. That's what we call LIFO, last in, first out. Perfect for reversing order, like when you're undoing steps in your code. For example, imagine you're typing a document and suddenly decide to undo. Your last few actions are popped off the stack and undone one by one. Now, contrast that with a queue. Think of a line at a grocery store where people join from behind but exit from the front. That's FIFO, first in, first out. Queues excel in scenarios like managing tasks or handling requests in order they arrive, such as printing documents or processing internet requests. Welcome back to our tech tutorial series. Today, we're diving into the world of data structures by understanding stacks and queues. Let's start with queues. Think of a queue as a line at a movie theater, first in, first out, FIFO. For example, if you have a queue, A, B, C, when you pop from the front using, it removes A. Now let's look at stacks. Imagine a stack of plates. Last one on, first one off, LIFO. In our code snippet, we create a stack with values 3, 2, 1. When we call, it removes and returns the top item, which is 1 in this case. So, stacks are perfect for scenarios like managing function calls or browser navigation history. Queues, on the other hand, are ideal for tasks that need to be processed in a specific order, like printing jobs or customer service requests. Hey there, ready for a quick quiz? Let's dive into which data structure is better for implementing a task scheduler. Here's the deal, we have queue where tasks are processed in the order they were added. Think of it like a line at a coffee shop, first in, first out. Now, why would this be useful for scheduling tasks? Well, consider a scenario where you need to run background jobs on a server. Each job is added as it comes, and each must wait its turn until the previous one finishes or moves through the queue. It's simple, fair, and efficient. So, which data structure fits best here? That's right, queue. It's the perfect choice for task scheduling in many real-world applications. Alright, let's wrap up what we've learned about stacks and queues. First off, stacks follow the last in first out, LIFO principle. Think of it like a stack of pancakes. Only the top pancake can come off first. For example, if you push 3 elements into a stack, 1, 2, 3, the next pop operation will return 3, then 2, and finally 1. On the other hand, queues use the first in first out, FIFO method. Just like a line for ice cream, first one in gets served first. If you enqueue elements, 4, 5, 6, the next dequeue operation will return 4, then 5, and finally 6. This principle makes stacks great for undo operations or browser navigation, while queues are perfect for managing tasks like printing documents.